The first example we look at to illustrate the sigma point Kalman filter is the same one that we looked at first with the extended Kalman filter. And if you remember, these were the model equations that the new state is square root 5 plus old state all added to w, and the output was x cubed plus v. And we're using the same process noise covariance and sensor noise covariance in what we do. And my hope here is to show you the code to implement an SPKF, just following the equations that we have derived, and to show you output from it that we can compare directly to the EKF. And in particular, I'm using exactly the same data. So even though the code here indicates that I'm randomly simulating the plant, these equations, in fact, I am actually in the diagrams that we see at the end using exactly the same data for the EKF and the SPKF, and I had used a code that combined both of these together. So we can see a one-to-one direct correspondence between the results. Here is the sample code. In the model, the number of states, the number of x states is 1, but in the sigma point method we need to come up with an augmented x which contains the x, the w, and the v, and w and v are also scalars, so the number of augmented states is 3. Number of outputs ny is 1. Then we define some constants for the SPKF method. I'm going to use the central difference Kalman filter constants, but you could choose to put in the unscented Kalman filter constants if you'd like here. I'm going to use a value of h equals square root of 3 in my implementation because that's known to be optimum with Gaussian noises. However, you might play around with that number a little bit because not everything stays Gaussian inside of a nonlinear function, so you might be able to achieve even better results with a different value of h. We need to come up with weighting values alpha m and alpha c. The central difference Kalman filter method has a different method for the 0th entry and all the other entries come together. So I really need to find only 2 values for alpha m and 2 values for alpha c to define the entire set. So h equals square root 3. The wm is the weight for the mean for x, wmx, weight for mean for x. And the first one is really the 0th entry, is h squared minus the number of augmented states, nxa, divided by h squared. And all of the others are 1 over 2h squared, as shown. And I'm going to use the same weighting coefficients for the covariance as I do for the mean, as is done for the central difference Kalman filter parameter set. In one part excuse me, of the code, I need to have all of these weights together in one vector, and so that's what I do here. I say I'm putting in the wmx1, that's the 0th entry that multiplies the mean, and then I'm repeating the others 2 times nxa times, so overall I have basically 2l plus 1 weights in this vector, and it's transposed to make it into a normal column vector here. Then I initialize the simulation. A lot of this is going to look very familiar to what we've already seen in the EKF example. I set sigma w, I set sigma v, I set the number of iterations. I make a random initial state as I did before. I set my estimate to 2 and my uncertainty of the estimate to 1, just as I did before. And the next thing that we do is I initialize storage for the true state and the estimated state and the estimated covariance matrix, just as we did before also. Now we start the SPKF loop. In step 1A, we do a lot of work because we have to build this augmented set of sigma points and so forth. So I've broken it down into steps 1A-I, 1A-II, etc. We didn't identify them as such in the text, but here it just gives you an idea that we're making some progress. The augmented mean is equal to the previous state estimate and the mean of the process and sensor noises, which are both 0. So that's x hat A for augmented. And then I want to get the augmented covariance matrix, which is, in MATLAB, I can use the block diag command to make a block diagonal matrix with sigma x being one of the blocks, sigma w being another, and sigma v being another. And then the square root, little s, square root of sigma xa is my Cholesky factor of sigma xa. And in MATLAB, I have to be careful to specify you want the lower triangular as opposed to the upper triangular Cholesky factor. Now we do something in the name of efficiency that is a little bit tricky. What we are trying to do, this capital X, is the augmented sigma points. It's a matrix that's tall and wide, and it's going to be 3 tall, so it has the X part, the W part, the V part, and then it's going to be you're going to have the mean here, the mean plus the Cholesky factor, and the mean minus the Cholesky factor in those elements. So there's really 3 wide each of those. So overall, I'm 7 wide. Now to do this, what I want to do is first take the mean, which is going to identify this first column, and copy it so that it is the basis underneath all of the columns. So I want to copy it so I have 7 of them horizontally and 1 of these means vertically. And I could use a repmat command to do that, as I did earlier outside of the program loop, to initialize a variable up here to repeat a matrix a certain number of times. However, there's a sneakier way of doing it that is much, much faster. So inside a loop, I would not use a repmat command unless I couldn't think of any other way to do it, because it's so slow. I did a profile once. MATLAB has a profile feature that you can time your code to see where it's spending most of its time, so you can try to optimize those lines to make them more efficient. And when I did that on a sigma point common filter, it was spending 90% of its time on one repmat call, which when I replaced it with this code here, my filter went 10 times faster. You know, it was almost 0 time when I replaced it. Very weird. So what am I doing? Well, x hat A is a 3x1 matrix, or a 3 vector. And I'm saying take x hat A, take all columns, and evaluate it at these columns. Say all rows. Take all rows and evaluate it at these columns. And the columns that I'm using is a vector of 1s that's 1 tall and 2L plus 1 wide. So this is equal to the vector 1, 1, 1, 1, 1, 1, 1. There's 7 1s there. So the output from this weird MATLAB syntax takes x hat A, all rows, and column 1, and it puts it in right there. And then it takes x hat A, all rows, and moves over, still column 1, puts it there, and so forth. And I'm just re-indexing column 1 7 times to make 7 duplicate columns in my output. And believe it or not, that strange way of indexing x hat A is immensely faster than the built-in repmat call, which is designed to do the same thing, only easier. Strange but true. The next thing I do is, so that matrix so far just has 7 copies of x hat A in it, and I want to add, to this column I want to add nothing, I want to add 0, but to the next columns I want to add the square root of sigma xa, I want to add the Cholesky factor, and to the next columns I want to subtract that. So that's what we're doing here. we're creating a matrix which is the matrix I want to add on to x hat, and that is h, the Cholesky factor, the gamma factor, which we've called h, square root of 3, times a matrix. The first column is zeros, the next columns are square root of sigma a, and the next columns are minus square root of sigma xa, and that adds everything together. So that one line, I guess spread over two, but basically one thought in MATLAB creates the augmented sigma points in a very efficient way. Then what I do is I want to create the prediction of the present state by taking the sigma points out of this matrix that correspond to the state and to the process noise and putting them through the state equation. So I need the prior state estimate and the process noise estimate, and I put them through the equation for the model for the state equation, which is square root of 5 plus the previous state plus the process noise itself. So first column and second column are used, and those give me the x sigma points for the present predicted state. I call those xx. And then I do the weighted summation of all of those using the sufficient multiply by vector scheme in order to give me the x hat, the prediction of the state right now. So all of that is step 1a, and most of it, frankly, is simply setting up the augmented sigma points up to this point, and then this here is doing the calculations of step 1a. Step 1b says I want to compute the covariance, the uncertainty of this prediction error. And what we need to do in the summation, we need to do the summation of alpha ci times xi minus x hat times that transposed. And I'm trying to do this somewhat efficiently in MATLAB also. We could use a for loop and go through every column of every sigma point and do it that way. However, I'm going to do it a little differently. I'm going to write the summation as equal to the zeroth value, so alpha 0c times x0 minus x hat times x0 minus x hat transpose, plus the sum from I equals 1 to p of alpha ic times those two terms. This part I can implement quite efficiently by taking this calculation, so I've got x0x minus x hat, and multiplying it by square root of alpha ic to make an intermediate variable, and then I have another square root of alpha ic times the other one. Basically, I'm basically squaring in a sense, and I can do all of that summation at once if I store stuff carefully in a matrix form. So I'm defining xs, this here is xs in the code, is the sigma points used to predict the state, not all of them, but from column 2 to the end, so these, not the first one, but the rest. And then I subtract out, again in a sneaky way, the x hat itself that I made, so I'm indexing that in such a way that I can subtract that vector from all of those sigma points. And I am then multiplying by a square root of the scaling, the weighting factor for covariances. So everything that there is xs. The reason I can't do that for the first term, the zeroth term, is that this weighting factor for the zeroth term is often negative. And if I take a square root of a negative number, I end up with something complex, and we have problems there. So I have to handle the zeroth term separately. So xs1, which is really the zeroth term, is the first one minus x hat. And then overall, sigma x is this entire summation, which I can implement efficiently as that matrix multiply of the matrix xs multiplied by the transpose of itself, plus adding on that additional term, the zeroth weight, times the XS1 times XS1 transpose. So that's a fairly efficient way to do all of that calculation in MATLAB without for loops. For loops are slow in MATLAB. This is probably not the first way you'd think of doing it. And what I recommend to all my students is whenever you see a piece of code like this, which is really quite difficult to understand, write your own code. So put this in, copy and paste it in, paste this whole example and run it, make it, make sure it works. But then also put in your own code using for loops or whatever, however you would code the mathematical expression in the previous section of notes to compute this. Put yours in and compare the two calculations. They should be the same. If they're different, then we know at least one of them is wrong. I think mine is right, but you can let me know if it's not. But that way it would give you some confidence that this code that I'm supplying to you is doing the right thing. And another thing you can do is put in breakpoints and print out variables and plot variables at different points in the code to give you an idea of, oh, that's what he's doing there. Please do that. Please don't just accept this code as, oh, there it is, it's given, it came down from the heavens in some way, so it must be right. Okay, enough said. As we've done many times now, we have to simulate the real system as well in this example. So I'm making a process noise, I'm making a sensor noise, I'm simulating the true measured output, I'm simulating the true state of the system. This is exactly the same as in the EKF code, no changes whatsoever. Now it's time to predict the output. So I take the predicted state of the system and I cube it, and I add the sensor noise from my augmented sigma points at the beginning of this loop. That's those are my sigma points. It's a bunch of them representing the output, and I do the weighted summation as we did for the state to get the predicted output. To get the Kalman gain matrix, I need to find sigma y and sigma xy with tildes on them. And these are covariance calculations like above, so I've got a sum of the alpha ci times thing minus mean times thing minus mean. So this is yi minus y hat, yi minus y hat, all transposed. This is the same, but it's going to be xi minus x hat times yi minus y hat transposed for the cross covariance. Same idea, so I do the same kind of steps. So you can go through there and see that's what's happening. And it's making overall the sigma xy and sigma y matrices that I need. And then finally, I compute the Kalman gain as sigma xy times the inverse of sigma y, and this divided by is MATLAB's shorthand for doing that in an efficient way. Last two steps are just standard. So estimate equals prediction plus gain times measured minus prediction, and covariance of the estimate is covariance of prediction minus gain times covariance of output times gain transpose. The rest is storage and plotting. No surprises there, I don't believe. And now we look at the output of the process. In the left-hand plot, I show the truth just as before. It's exactly the same as the truth in the EKF example because I use the same data. And the SPKF estimate as a blue solid line and the bounds as blue dashed lines. And looking at the left plot only, we see again the SPKF is tracking the truth pretty well. And the error bounds are also encompassing the truth most of the time. Not all of the time, unfortunately, but at least most of the time. It's easier to see in the right-hand plot where I'm plotting the errors. So I resurrect the green line, which is the EKF error for the same data set, and the EKF bounds are the dash lines. And then I put on the blue line and blue dash lines for the SPKF equivalent results. You could argue whether the EKF or SPKF are producing better estimates, because the EKF is always a little bit negative, and the SPKF is always a little bit positive. I think the SPKF is doing slightly better because this pulse here of error that the EKF did, the SPKF did not do that. Although here they're pretty similar, and here they're pretty similar also. So the SPKF prediction, or estimate rather, may be better. I think it is a little bit better, but it's not a lot better. But what is enormously better are the SPKF error bounds, which is a little bit funny thing to say just looking at it, because if I looked only at the error bounds, you would say the error bounds are far worse. These are lovely tight error bounds, and these are awful large error bounds. Well, that's not what I mean. I mean that the SPKF error bounds are far more useful than the EKF error bounds, because almost always the SPKF error is inside of the error bounds. This is an exception right there. I've got 2 points out of 40 that are outside of the error bounds, whereas maybe the majority of the EKF points are outside of the EKF tiny error bounds. This is one reason I really prefer the SPKF, because error bounds are important if I want to do a conservative calculation of how much power is available in a battery pack. I'm not going to use the state of charge estimate. I'm going to be using the state of charge estimate minus an error bound so that I could get a conservative estimate of discharge power, or state of charge plus error bound if I want to get an estimate of charge power. And we'll see all of that again, of course, in Chapter 6 and 7. But the error bounds are really important, and here the SPKF error bounds are improved. As we did before, we looked at a simple EKF example, and what we're going to look at next is a more complicated SPKF example where we implement the filter onto the battery model and see how it performs there.